And hello everyone, um, welcome back to our Spalart Allmaras turbulence modeling videos. So in this video we're going to continue our discussion. So the question is all right, last video we were talking about the functions in the log wall region, right? It seemed to work well as long as you have a correct wall function for the viscous sublayer. So in this video we want to ask, how do we deal with the viscous sublayer, and how can we force this sort of velocity profile and the correct turbulence viscosity profile in the viscous sublayer. And also after that you want to deal with the buffer layer as well. Okay, so how can we have the correct turbulence viscosity treatment? Okay, so according to this paper, it says that in the log law region, you have a nu t equals to kappa y u star, right? And y is the distance from the wall, u star is this friction velocity. Okay, so y is this friction velocity, right? But in the viscous sublayer, this doesn't hold true. So how can we get it to work? So to get the correct turbulence viscosity in the viscous sublayer and in the turbulent regime, to get the correct term, we use another damping function. So the basic idea is to take the kinematic viscosity above, which is the log law region, correct kinematic, turbulent, I'll make it turbulent kinematic viscosity, and then we dampen it. Alright, can we take the kinematic viscosity above, over here, and then we dampen it. So in the viscous sublayer and buffer region, we have this. Okay, we have ky into u star. Alright, and then we try and multiply it by some damping function. Okay, so I mean, long story short, damping function looks like this. This is the fv1, which is a damping function, and that is equals to chi cube over chi cube times some constant to the cube. So fv is named as such because v stands for viscous, and chi, this function chi, is equals to kappa y plus, equals to kappa y plus, right? So chi equals to kappa y plus, and if we were to look at this, function in the log law region, and we divide it by nu, okay? All right, so this divided by nu equals to kappa y plus, because this term y u star over nu, that is actually that's y plus. So this is equals to chi. So the other way of writing is that this kyu is some function. This is like the turbulence viscosity, but we don't say this is the turbulence viscosity anymore, because that's not what it is. So in the paper, we use the term that this turbulence viscosity here, this only correct in log law. Okay, so let's disclaimer. All right, so disclaimer is this: the turbulence viscosity nu t in the law region, and the majority of the fluid, or the bulk region of the fluid, is called, okay, we use the term nu tilde. So that's why inside this Spalart Allmaras equation, we see that it says there's a viscosity-like variable nu tilde. So in fact, the nu tilde is actually turbulence viscosity inside the bulk region and law region. Law region. All right. So sometimes you will see chi written as such. So this nu t here is actually this nu tilde here. So sometimes you will see in the literature it will look like this: nu tilde over nu equals to kappa y plus. All right. So hopefully that clears up confusion. Chi is defined as kappa y plus, but of course, since this in the law region is actually this. In the law region, this turbulence viscosity nu tilde is actually this kappa yu star. It will actually equals to chi in the law region. Okay, so this only holds in the law region. Only holds in the law region. I mean, that's where you have your damping functions anyhow, or rather definition starts in the law region. Okay, so that's how this chi actually comes about. Okay, right, so chi actually comes about here. So what our equation now looks like. All right, so we won't use the term nu t anymore. We won't use the term nu t anymore. We will start using the terms nu tilde. So nu tilde is actually the viscosity in the law region and the bulk fluid. So we will use nu tilde everywhere we go now in this transport equation. Okay, so nu tilde square. So this looks more like our Spalart Allmaras equation. Okay, so this is the Spalart Allmaras variable nu tilde. All right, so this actually is here so that we can do the wall function thing over here. So how do we do the turbulent viscosity? It is as follows: nu t equals to nu tilde times some function. So this is the wall function that helps it to get the correct value inside the what do you call that? Inside the viscous sublayer region. So this is what it's supposed to do. All right. So it's yeah. So however, there are a few other things, few other problems. Firstly, there's too much production of turbulence in the viscous sublayer. So even though you kind of have this relation to try and dampen the actual turbulence viscosity inside the viscous sublayer, the production of turbulence is still too much. Production of turbulence in the viscous sublayer. So what they do is to dampen the production term here. So this is the production term, and what they do is to dampen it. How do they dampen it? Well, they use this kind of a relation. They replace s in the equation. So they replace s with some s tilde. So we replace s with s tilde where S tilde, okay, is a modified function of S. Okay, so S tilde is some modified function of S, and it will be dampened. It will be dampened towards 0. I mean, of course, it will be dampened towards 0 in the wall. And how do we dampen that? They use this form. All right, so S tilde is, I wonder where that equation keeps jumping to. Okay, S tilde equals to, all right, S plus nu tilde, S plus nu tilde, kappa squared d squared. If you remember where that term comes about, we saw earlier, actually this is very similar to this term. Kappa squared d squared kind of appears here. However, the length on top is slightly different. Okay, so it's a nu tilde only, right? Nu tilde on top to kappa squared d squared times some FV2, where FV2 equals to this. All right, and FV1 kind of is used again, or rather, yeah, it's used again. Right, so this is FV1. FV1 is some dimensionless function for the viscosity. All right, FV1 is this. This is our damping function. So FV1 is here. So again, yeah, this is to help dampen the production term inside the viscous sublayer. So now our equation looks like this. Okay, so our equation looks like this. There'll be a S tilde here, S tilde. So replace S by S tilde, and this is to make sure it kind of gets the correct behavior inside the wall. So the wall functions are all hidden in this, in the turbulence viscosity term, and then this production term as well. All right. Okay, so next thing, to balance it out. Okay, to balance it out. Okay, now that we artificially reduce production of nu tilde, not nu t anymore. We artificially reduce production of nu tilde in the boundary layer. We also need to reduce the destruction of nu tilde, which is the turbulence viscosity in the log law region and the bulk layer. But towards the wall region, we just leave it as it is, so that it's easy to calculate. Then we just dampen using these damping functions to get the actual turbulence viscosity. Alright, so we also need to reduce the destruction of nu tilde just to ensure everything is it's balanced out correctly. Because you reduce the destruction, you also need to reduce this by roughly the same amount, so that it kind of balances off nicely. So that's what is being described here. Okay. So that's what this CW1FW is about. Okay. We finally okay, actually this one comes a lot later. I kind of lost. Yeah. Okay, this one actually comes a lot later. Not here yet. I kind of introduced this a little early. That should be in this part. Okay, so anyway, sorry. Yeah. So anyway, to make sure, okay, just recap. We have our transport terms here, the substantial derivative here, and then we have a destruction term which we are supposed to damp. Okay, I forgot to add the damping function, which is FW, F wall. Okay, F wall is here. So F wall is here. Then we have our destruction term here. We have our source term here. Then we have the diffusion term here. We explained why that was the case. Okay. So now we have, so far we have dealt with, okay, the log law region, the viscous sublayer, and we also dealt with the bulk region. Okay, this is the bulk region. So log law region will have the nil tilde definition. That's why it comes about. Viscous sublayer, wait, no. Viscous sublayer is the nil tilde region. Log law region is log law region is kind of correct by itself already. With FW. Okay, so that helps it with the log law region. Alright, so FW helps with the log law region. Nil tilde and S tilde deal with the viscous sublayer region, and this is how we are so far. So basically it's all well and good so far. However, there's still another problem. Okay, the problem is with numerical instabilities. Yeah, the problem here is with numerical instability inside the laminar region. Okay, so we have numerical instabilities in the laminar region. Okay, so this is the problem. Numerical instabilities present in this formulation. Alright, so this is the part 2.5, and the long story short, having nu equals to 0 usually causes the solvers to blow up. I'm skipping all the explanations here. Alright, I'm skipping all the explanation here to kind of cut the long story short. Blah 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 blah. So okay, so the main problem is with this numerical instabilities, and also the and especially it's important in the laminar to turbulent transition for laminar region shear layers. That's what it said there. What is the shear layer? You can look at Thermopedia. Basically, a shear layer is somewhere where anywhere there's a velocity gradient like this, a strain, a place, a layer with this, with a strain here, is called a shear layer because there is presence of shear stress. Okay, this is the presence of shear stress. That's why it's called a shear layer. Okay, so well, numerical instabilities in this region, and of course the problem of transition, it necessitates us to set a trip. Okay, it needs to set a trip to prevent instability. So the idea is to allow the nu tilde, okay, it's not turbulence viscosity anymore, it's just a nu tilde to become 0 in the viscous sublayer, and to have a stable solution and not cause blowout. So what we do to ensure this stability is to artificially dampen the production term to zero. Artificially dampen the production term to 0 in the boundary layer. Okay, however, to ensure that okay, this turbulence won't go negative, but okay, no, delete this part. Okay, now that we artificially reduce the production of nu tilde in the boundary layer, we also need to artificially reduce the destruction of nu tilde in the boundary layer and transition region. Okay, so how is this done? It's done with the use of these trip functions. So this is one of them, the trip function. Okay, ft2. Okay, ft2 equals to, okay, well, why not I give you the big picture first. The trip term, where do these trip terms happen? So to artificially reduce production term, So they introduce a trip term here, 1 minus ft2 in here. This is where the trip term is done, and to artificially reduce the destruction term, they introduce yet another term here. So this will be, alright, this, whatever this term is here, C wall 1 FW, alright, C wall 1 FW, okay, minus, okay, CB1 kappa squared over FT2. Series activating unnecessarily, but anyway, CB1 kappa squared, and then you times this FT2 here, FT2. So this is another the constants, the basic constant, divided by the von Karman coefficient, about 0.41, and then this is the damping function. Right, this damping function. All right, what does this damping function look like? Okay, so anyway, before that, remember, this damping function is simultaneously supposed to destroy this turbulence viscosity destruction term and production term in the boundary layer, so as to ensure numerical stability. So this is purely for numerical stability. There's no, I mean, it's not very much of a theoretical modeling thing here. It's just to help the solver do its job well. And what does FT2 look like? Okay, FT2 looks like this. Okay, FT2 equals to C3 equals to T3. All right, times exponential of minus CT4 minus CT4. These are they call them the trip terms because they activate the trip so as to prevent the numerical instability. Alright, so the trip terms, okay, T stands for trip, okay, exponential CT4 into chi squared. Alright, so this ensures that it gives the proper wall behavior, because chi squared is it's got to do with this wall function anyhow. Okay, so remember chi squared looks like this, or remember chi looks like this. Okay, so this has to do with the y plus. So that's why you have this down here, so that you can destroy these terms at the wall, or destroy this destruction term and this production term at the wall. So if you can see, when y plus equals to 0, chi equals to 0, and this term becomes 1. Okay, so you'll have a minus CT3 over here. Alright, minus CT3 over here, and that will help to destroy this term. Okay, so I'll stop for now. I'll continue more discussion on these trip terms in the next video. Thanks for watching.